So welcome everybody. I hope you can hear me. So my name is Helena and I will now show you how to analyze a single session using the Vienna VieVS satellite software. I prepared two sessions which we can analyze. The first one is the R&D session, and if there is enough time in the end, we can also analyze the R1 session. And I also prepared a handout which you find on the VieVS wiki, so you can download it there. And in this handout, so there are all steps which we are doing during the analysis described, so you can always have a look at the handout. I will show you the handout here. Okay. So that's the handout. Can you see? Yeah. So there are all steps described and also some screenshots. So you can definitely have a look there. And also if you want to do the analysis later again, you can do it with this handout. Okay, then I would suggest to start. I will now show you the session which we will analyze. So the session is the R&D session, and the start date is the 8th of May 2019, 5:30 p.m. It had a duration of 24 hours, and there were in total 8 stations participating. Here in this figure, you see the network. And now I would suggest that we start MATLAB. So I will start MATLAB here and try to change the screen I'm sharing. So I hope that everybody downloaded already the VieVS. So the VieVS package. And it's important that you have exactly this structure here. So the common folder, a VieVS folder, and a VieVS_opt folder. So if they have a different name when you downloaded it, then please change it to exactly these names. Otherwise, you will have some problems. And now, now you can see my MATLAB. And now I hope that everybody has opened the MATLAB. So here, it's important to have the right path here. So go to the folder where you have downloaded these 3 folders. And now navigate to VieVS, and then one more to the folder work. So, and here you have this file vievs.m, and this we will use to start VieVS. And this can be done by simply typing here VieVS to the command window. Now when you press enter, the graphical user phase of VieVS is starting. This might take some time. Okay. So I think I have to share it again. Now you should see my VieVS. Or I can maybe, okay. And so that's the start page of VieVS. Here on the top, you have the different menu points. And we will go through the menu points which are necessary to analyze a single session in detail. And yeah, so the first one, so first we need our observations. So we have to load our VieVSDB file. So this can be done by here, clicking on File, and then taking the first option, Set Input Files. Click on it. And now here are all the options to load data or to load the observations. There are different options like to browse for a session or to browse for a process list. And there's also the option to browse for VieVS files. So we are taking this button because we have a VieVS file. When you click on this button, then another window is opening where you can select the files. The session we are analyzing took place in the year 2019. So here it's structured in per year, in folders per year. So we take the 2019 folder and we take the session May 08 because that's the right session now. You click on the add button and now this session is added to the selected items here. If you took the wrong one, don't worry, you can, if you click on the session, then the remove button appears, so you can remove it again. You can also add here more sessions, but in our case, we are fine with this one now. And if you're done, you can click on the done button, and now the session is added to the process list here. Yeah, so now we will create the op file. I will show you the op file in a second, but in order to use it, we have to check this box here, use opt file. Now we change here the folder from default because that's the default folder, and there is a other folder, webinar. So when you have this, then you can create or open the opt file by clicking right on the session here and take the first option, open create opt file. Click on this. And now the opt file, I have to share again the screen. Now you should see my opt file. That's empty by now because we haven't done anything. But yeah, the op file is a file where all the information which is done during the analysis is stored. For example, if you detected some clock breaks, they are added here. If you exclude a station or a baseline or a source, it's written down here. If you want to downweight a station, or if you don't want to use the cable call, then it's specified here. Here in the bottom, you find some examples how things are done, like how's the format. For example, if you want to set the clock reference to the station cell, it's done in that way. Or if you edit clock breaks, then it looks like this. And if you want to remove it, you can simply delete this line, but then also make sure that you change the counter here. Yeah, you can exclude stations completely by just typing the name, or partially by defining the time span where you want to exclude the station. And same, so you can exclude baselines and also sources. Here again, you can exclude all observations to a source or partially. And yeah, here you also see how to write it when you don't want to use the cable call information for a station. Okay, now we will close this opt file again, but we will need it later. So I close it. Oh, okay. Okay. I go back to my VieVS. So you now see my VieVS again. And I will show you where you find the op file in the folder structure of VieVS. For this, so here in this, I just opened the directory where I have the 3 folders of my VieVS version. And now if you go to the VB opt folder, then you have the 2 folders which we just saw. Now take the webinar folder, and now 2019, because that's the year of the session. And now here you have the opt file stored. So if you ever want to look for the opt file, it's in this folder here. So now we will go back to VieVS. And so now we loaded our observations. So we have all the observations, and now we also need the theoretical delays. The theoretical delays are, so the models which you use or need for creating the theoretical delays are here under the tab models. There are different models, and we can have a look at, for example, the troposphere. So here you have all the options for modeling the troposphere at the time of observation. Yeah, heterostatic delay, and here are the different mapping functions which you can use. You can also have another look on reference frames. So in this option, you can set which reference frame you want to use. So in this case, we have the ITRF 2014 for the terrestrial reference frame and the ICRF3 for the celestial reference frame. And there are a lot of other models, for example, station models. We can have another look for station models. Here you can, for example, deselect if you don't want to correct station coordinates for the solid Earth tides, but we want to select it again, or which model should be used for correct the station coordinates because of tidal ocean loading. Yeah, there are a lot of options, but the default options are usually already pretty good models. So if you don't change anything, it's also good. Okay, so now we have our observations and we have everything set for creating the theoretical delays. And so now you see the system. The system can be seen as to have two streams. So on the left, there are the observations, which undergo some instrumental and some environmental corrections in order to obtain the reduced observed delay here. And on the right stream, there are, starting with the a priori station coordinates and with the a priori source coordinates, there are the theoretical delays created using different models. And then you have the theoretical delay, and the two streams converge at the entrance of the least squares adjustment. The least squares adjustment theory allows the estimation of unknown parameters in an overdetermined system of equations. And in our case, we have now a single session. It's possible to estimate these parameters. So station coordinates, source coordinates, Earth orientation parameters, the troposphere, and clock parameters. So here again, you see the list of parameters which can be estimated from a single session. So now there's the question, how do we estimate them in VieVS? In VieVS, these parameters are estimated as continuous piecewise linear offsets. And this means that we estimate the parameters in an interval, for example, every 30 minutes. And between two estimated parameters, we are doing a linear interpolation. I will show this a bit more in detail on the next slide here. So let's say we are estimating the parameter at time 1. The estimated parameter is x1. And now, half an hour later, it's time 2, we estimate it again. And in between these two parameters, we have a linear interpolation. So if we are now interested at the parameter at time t, which is between t1 and t2, we can simply do it by using this linear interpolation between the two estimated values. And in order to avoid singularities and also to do some improvement, it's possible to introduce constraints, so-called pseudo-observations. We distinguish between relative constraints and absolute constraints. The relative constraints tell the least squares method that the value for the next estimated parameter can be only a certain value away from the previous one, so that they don't vary that much. And the absolute constraints tell the least squares method that the value of the estimated parameter is only a certain value away from the a priori value. And now I would suggest that we have a look on how the estimations settings are set in VieVS. For this, we can go back to the VieVS GUI. And yeah, so the next tab is the estimation tab. So when you click on it, then you see least squares, because we're doing a least squares adjustment. And here you have again the list of parameters we want or we can estimate. So the first one is troposphere. We can have a look on this. So for estimating the troposphere, we can estimate the zenith wet delay and also northern gradients and eastern gradients. If you don't want to estimate, for example, zenith wet delays, you can simply uncheck this. But yeah, we want to estimate it. And here you can set the interval. By default, it's set to 30 minutes. And here we introduce some relative constraints. And the constraints are 1.5 centimeters after an hour. The same settings are here for the northern gradients. Again, the interval, it's larger, so it's longer. And here we have some relative constraints, but also some absolute constraints. We can have another look on the clock. How is the clock estimated? So the clock is estimated as piecewise linear offsets, one rate and one quadratic term per clock. And the interval is 60 minutes. And we also introduce some relative constraints, which are 1.3 centimeters after an hour. Yeah, we can have another look on Earth orientation parameters. So we estimate all 5 of them. And the interval is 1,440 minutes, so 1 day, 24 hours. And the constraints are pretty tight because we don't want that much variation. Yeah. And yeah, there it's also possible to estimate station coordinates and source coordinates. Okay. Now I will go back to my slides again. So how is the least squares adjustment done in VieVS? It's done iteratively. So first, there is a so-called first solution calculated. The first solution has a reduced number of parameters, especially the clock. There's only one offset, one rate, and one quadratic term estimated for the clock. Therefore, it's pretty important that you want to look for clock breaks. You always have to look at the first solution. In the main solution, the results from the first solution are used as new a priori values, and all parameters are estimated as piecewise linear offsets. Okay, then we can have a look on the settings in VieVS for the least squares method. You can find these settings at the tab Run. And then here you have the second option, VieVS estimation settings. Click on this. And then you come to the page where you can set everything. So here there's the first solution where we can see that there's one offset, one rate, and one quadratic term per clock. And here you have the main solution, and there is everything is estimated as piecewise linear offsets. So all parameters are estimated as piecewise linear offsets. Okay, So now we have everything. We have our observations here. We have the models to create the theoretical delay. We set all the parameters for estimating. Now we can do the analysis. So go and click the button Run, and now to run options. Okay, so here you see the list of modules from VieVS. To analyze a single session, we need the VInit module, the VMod module, and the VLSM module, so exactly what's checked by default. The VInit module is initializing everything, so it's loading the observations. The VMod module is doing the observation modeling, so there all the models which you set are taken in order to create the theoretical delays. And the last module is the VLSM module, which is doing the least squares parameter estimation. And yeah, so now we define here a subdirectory so that you can find your results later more easier. And I will simply take the name of the session. So it's a RD session and this, but you can take anything you want. Okay, now I would suggest that you can simply start the calculation by clicking on the button Save and Run. Now MATLAB is doing the calculation. And you see here in the command window, there is some output. I will just wait until it's done and then we can go through it in detail. Okay, so let's start from the beginning. Okay, so first, welcome to VInit. So the VInit module is starting here. All the data is loaded. So there are 8 stations, 50 sources, the number of scans, and in total, more than 2,000 observations. And yeah, so it loads all the observations. Then it's successfully finished, and the next module is starting, the VMod module. Here, the theoretical delays are created using the different models we set, for example, here, station corrections, and so on. And when this is done, the last module is starting the so-called VLSM module. And now the discrete method is doing the calculation for parameter estimation. So here we see the number, again, the number of scans and the number of observations to load the data. Then it's forming the weight matrix. And here you have a list of the number of observations from the different antennas. Yeah, a lot of calculations are done here. Here you have the total number of estimated parameters. So in total, 869 parameters are estimated. And here you have a list of which parameters are estimated and the number. Okay, then here in the bottom, you see the result of your solution and the chi-squared, it's 56.161. So the chi-squared indicates how well the models fit your observations. And 56 it's high, so it should be around 1 usually. So we see that there is something to do during the analysis. Okay, now I would suggest that we have a look on the residuals. For this, we go back to the graphical user interface. Yeah, and okay, first I will tell you something about the modules. So the vinit and the vmod module, it's only necessary to carry them out once, because MATLAB is the data is stored. So in order to save some computation time, you can deselect these two models and just run the VLSM module again. Okay, and now we can have a look on the result. For this, we go to run, we go to plotting, and then to residuals. Now we have here to look for the subdirectory we just created. So there is whatever you chose for your directory, and then you click the load button. Now the residuals are loaded, and we see, yeah, the chi-squared is high. So let's look for some issues. So here, they're the residuals in centimeters, and this should be normally distributed around 0. And each dot here is an observation. So for example, this dot here on the top, it's the baseline between Matera, and you find the same dot, also the corresponding dot at the bottom, because it's like mirrored. So this observation is between Matera and Sheshan, because here it's the brown one, Sheshan. And the same for this dot, for example. This is the observation between Koki and Sheshan. Okay. In order to fix some issues, it's good to look through the residuals, and you have the option to look through them per for example, baseline, per station, and also per source. Let's look through them per station. And here at the top, you can switch between the result of the first solution and the result of the main solution. You remember that the first solution, there is a reduced number of parameters. So I will go to the first solution, because there it's definitely easier to, so there you can detect clock breaks. And yeah, we will have a look now if there are some clock breaks. So we take the first solution, and then we go through the residuals station-wise. Okay, so for Telesa, there are no jumps. Then Trau, Robert, Koki. Okay, so here you definitely see that there is a jump here. Then it's jumping down. Then it has again a strange drift up there. And then it's jumping again. And then it again has drift. So that's definitely a clock break here and here. Okay, let's look at the other stations, and then we can insert 2 clock breaks. Sheshan, there are no jumps, and Betzel, there are also no jumps. Okay, let's set the 2 clock breaks at the station Nyolesund. For this, I would suggest to zoom in a bit. You find the zoom in here on the top, and just click on it, and then you have the option to zoom in. Just this window. Okay, now we see this jump here. Okay, if you want to add a clock break, you have here on the left the section clocks, and there's the button add clock break. So click on this button, and now your mouse is changing to a crosshair, and you can set the clock break. I would suggest that it's somewhere here. And now when you click your mouse button, it's asking you, do you really want to insert a clock break? And yes, I confirm this. Yes. And in order to insert the second clock break, we zoom out a bit by using this here. Just double click, then you're again have all the residuals. And now let's zoom in to the other clock break. So that's actually a pretty nice jump. So exactly. Now unclick the zoom button and click again to the add clock break button. Now again, the mouse is changing to a crosshair, and we just go between the, so somewhere between the jump, doesn't matter where exactly, and click your mouse button. Then again, confirm that you really want to insert this clock break. And the second clock break is written into your opt file. I will now show you how the opt file changed. For this, we go to, so again, here you have the 3 folders for your VieVS. And now where I showed you before that in this folder, there are all the opt files stored. So we go in this folder and then in the webinar folder, and then 2019. And now, yeah, there's only one. We take this one because that's for our session. When you open it, you see that there are now 2 clock breaks added automatically for Neolus, also automatically created Neolison, and here the modified Julian date where we just set it. Okay, I will close it. No, I will go back to VieVS. And now we set the clock breaks. So when we now press the save and run button again, VieVS is doing the least squares adjustment again. And now it considers the 2 clock breaks. And now the 2 jumps should be gone. Okay, when you have to reload it. So when you press here on the load button and choose the right session, and then you go to the main solution, then we see that the chi-squared, it's already a bit smaller, so 51 instead of 56, but still there is some issue. Okay, but now when we go to the first solution again and have a look at the station Neolison, where we had the 2 clock breaks before, we see that they are gone, because now they're like, here at the first part there's a clock estimated, then in the middle there's another clock estimated, and wherever there's the second clock break, there's another clock estimated. So now this looks pretty good. There are no clock breaks anymore. Okay, but as I already said, the chi-squared is still high, so we have to look for some other issues. And when we go through the residuals from the first solution again, we see that they are all like normally distributed around 0. But that's not really the case for Sheshan. When you see it, that's like, it's pretty noisy, and it's not like at the other stations. Maybe when I zoom in a bit, you see it better. Because when we now compare it to Neolison, we see that there it's definitely around 0, but Sheshan, that's not the case here. This can be the sign for that something went wrong with the cable cal measurements. So there went something wrong with the cable cal measurements, and when we apply this, it's degrading the solution. if we want to have a closer look on the cable color information, we can go back to File and to the section Set Input Files again. And now you have here the possibility to look at the NetCDF analyzer. So this can be done by right-click here again. And now we take the third option, Analyze NetCDF file. When you click here, the NetCDF analyzer is opening. Genau, das muss ich auch sharen. Okay. So you should now see this analyzer. And this database is, the content is structured in different folders. So first we have to select the right session. In our case, the session was session. So we take here session 25. And the cable cal measurements are stored in the folder stat. And now we have to take the right file, and the file is called cal cable. Okay. Now, when we want to plot the cal cable, also the cable cal measurement, you have to click here on the variable. And now the data is plotted here. We see that this is pretty noisy, and also it's 10 to the power of -9. When we compare it to, for example, the station Matera, and now plot it again, we see that that's not that noisy, and it's also smaller. So yeah, that's also a sign that there was something, that there was a problem with the cable cal delay measurements. Okay, so this means that we can simply try to don't use the cable car measurements, and we can have a look if the solution is becoming better. So I will go back to VieVS again. And I will now show you how to ignore the cable car information. Okay, we have to specify this in the opt file, so we need to open the opt file. Again, this can be done by right-click here on the session and open the opt file. Okay, so here at the bottom, we have the option to ignore cable cal. So we want to ignore it for one station. And now we have to type the name of this station. Sorry, I forgot to share the right file with you. Okay, so now you see the opt file. And here at the bottom, you see that we want to ignore cable cal for one station. And now you type the name of the station. Okay, so Shisham 25. Okay, we save this. And then it's important that you close the ops file again. Because, okay, go back. If you don't close it, if the opt file is still open, then you're then it's not possible to click on the GUI. So it's important to close it. Okay, now we said that we don't want to use the cable cal information for session, and we can now do another run, and we can see if our solution becomes better. Okay, so let's have a look at the result. Plotting residuals. And now load it again. Go to the main. And now we see that the result is already much better. So it's 3.120. And when we go to the first solution and go to the station Seshan, we see that it's now much more normally distributed compared to before. Yeah. Okay. So now when we say, okay, there is nothing else to do for...
Excuse me.
Yes.
Can you please repeat the part after saving the OPT file?
Okay, yeah, I can do this.
Thanks.
So, okay, let's go back to the opt file. So files, set input files. And now open create the opt file. Here, I have to share it again. So now you should see my opt file. So there are already the 2 clock breaks, which we just inserted. And here you can write that you don't want to use Seshan as, so no cable color information for Seshan. Okay, I hope it's clear now.
Yep.
Okay, and then close the opt file again, and you can go back to your VieVS. And yeah, we can have another look at the residuals.
So I need to run again?
Yes, yeah, okay. So now you need to run it again here with the button save and run.
And
then,
when I'll run this part, then what are the settings for the run VieVS INIT and mod? It will be the same, or this time I'll run with the LSM?
Yes, so it would be the same, but it takes a bit longer. So if you want to save some computation time, you go to run options, and then you can deselect these 2 modules because they only have to be carried out once. If you haven't done it before, then you should do it because it's not possible. But if you already run these 2 models, then you don't have to run them again. So you can save some time when you deselect them. But it should be the same if you select them. It's just a bit longer. Okay. So we can go back to plotting and residuals. Load it again. And now we see that it's already much better. So it's from 51 to 3. And now when we look through the residual station-wise, we don't find any issues which we can fix. So we can say, okay, we are satisfied now, but we still have to do the outlier. We still have to remove outliers. To remove outliers, it's a 2-step process. First, we have to detect the outliers, and in a second step, we have to remove them. Okay, I will show you how you set it to detect them. This can be done in the section run, and then here VieVS estimation settings. Click on this. And now you have here in the main solution, you have the possibility to do a simple outlier test. So we check this, and now we run it again with the button Save and Run. And now we can have a look again at the result with plotting residuals. Load it. Was it? Okay. So usually it should mark the outliers with black crosses here, but it seems that there are no outliers. So, but was it, did I will run it again. Maybe there was something not set. Okay, so we see that it did the outlier. Okay, I will show you this in the MATLAB. So we now see that during the VLSM part, there it's detecting outliers, but there are no outliers found. So we don't have to remove them, but for completeness, I will show you how to remove them. So let's say that we found outliers. So we don't want to run another outlier test again. So we deselect this. And now we want to eliminate them. This can be done under the tab File and Set Input Files. I have to, sorry, I forgot to change my, to share the right window with you. Okay, I will repeat the last step. So we go back to Run VieVS Estimation Settings. And now we deselect this again because we don't want to run another outlier test. We already did it. And now in order to remove the outliers, we go to File, Set Input Files. And now here we have the possibility to eliminate them. So we click on Eliminate the outliers. And now when we run it again, we click Save and Run. Okay, so now if there would be any outliers, they would be removed. But yeah, so we can say that it's it's normally distributed and we don't have any big issues or any issues. We didn't see any issues in the station-wise residuals, so we can say that we're done. I will now show you where you find the output. So for example, the parameters we estimated. So this can be seen here under plotting and then parameters. And here you have again to select the right folder, the so-called RD folder, and load the parameters. And here you can plot different parameters. For example, the zenith wet delay for the station Fortaleza. It has the unit centimeters. So here each star, it's an estimated parameter. So zenith wet delay was estimated all 30 minutes. And in between, we are doing the linear interpolation. We can have a look for the same for cookie. It looks a bit different. And it's important to note that these values are always additions to the a priori values. You can also, if you're not satisfied here with time on the x-axis, you can change it here with time reference format from modified Julian date to, for example, hours since the session start. So here 0 hours, 5 hours, and so on. Or you can also change it to minutes since the session start, or even to seconds. But yeah. Okay. It's also possible to add the error bars. So if you're interested in the accuracy of this parameter, you can have a look on the error bars by clicking this button here, or this option here, show error bars. And now there's always the error bar added to each estimated parameter. If you now want to save all this information in a text file, you can also do this by using the button here, Save Values As. When you click on this button, then it automatically navigates to VLBI out folder. And here we can simply type, I have to, okay. I will share. Okay. Yeah. So here you can type in the name what you want. So you're automatically in the VLBI out folder. So I will just type it, so name it Zenfed delay. Now we save it. And when we have a look at the result, we can navigate to VLBI and to the out folder. And here we find the text file. So it's Zenfed delay. And here we find the parameters, so always the time, the value, and the standard deviation. You can now use this file for analysis. Okay. And another output which you can use is stored in VLBI and then in the folder data. And then you have to go to the folder level 3. And then you find again the directory which you named when you run it. And here you find several MATLAB files. So for example, so there's this file x underscore, and in this file, or in this MATLAB structure, there is all the information stored, so all estimates and the accuracies, and you can simply load this file in MATLAB and do some other analysis or plot the data or whatever. So that's definitely pretty useful to use this file. And another output which I want to show you is the Sinex file. You can create the Sinex file by clicking here, Run, and then here you have the option Sinex output. Here you have to specify that you want to create it, and if you create it, then you have here different options what you want to include. For example, okay, I want to include the tropospheric gradients, but I don't want to include Zenfed delay. So you can do this with using these radio buttons. So Sinex, it's this standardized output format for distributing data. Okay. That's everything I wanted to show you with this first R&D session. And I will go back to my slides. So here is another overview about the different outputs after analyzing a session. And maybe before we start analyzing the next session, are there any questions which you just want to ask? Or yeah. Yeah. If not, then we could make a short break and continue with the next session, the R1 session. Yeah.
May I ask a question?
Yes, of course.
Yeah. When we try to remove residual on everything and the chi-square is lower than what it was at the first time, for the main solution, we can see it for the first solution is getting higher. For example, well, what's the reason? I don't understand why for main solution it's getting lower, but for the first solution it's high. You can check it now, it's 471 when we are looking at the plotting residuals. Can you see that?
Yeah.
Maybe it's a silly question, but I suddenly noticed that.
Maybe the reason for this is that in the first solution, there's a reduced number of parameters, and if you remove some observations, then the estimation is a bit worse. But yeah, so I think the more important thing is that the chi-square of the main solution is decreasing.
I see. So we have to check the main solution always.
Yeah.
Okay, cool.
Yeah.
Thank you.
You're welcome. Okay. If there aren't any other questions, then I would suggest to make. Okay, there's another question.
May I ask? Yeah.
Yeah.
If we have a lot of session,
yeah.
Because normally we have 6,000 graph. Do we need to check the clock break of each session, or is there a possibility to make it more automatically?
No, the clock breaks. You have to look for the clock breaks. It's not possible to detect them automatically. So yeah, if you have more sessions, then yeah, you have to go through all stations if you want to detect the clock breaks. Okay. So if there isn't any other question, I would suggest to make, let's say, a 2-minute break, and then we can continue with the next session. Thank you very much. Okay, I hope everybody is back and we can continue with the next session. So here there is a short overview about the next session, which we will analyze. It's the R1 session, so the IVS R1 885 session. It started at the 11th of March 2019, and at 5 p.m. it had a duration of 24 hours, and in total 8 stations were participating. In this figure you see the network. Okay, then let's start with the analysis. So we again need VieVS, and we can now clear this session because we don't want to analyze this session again. So clear selected. Okay, I hope that everybody can see my screen now. Yeah. So I just removed the session which I had in the process list here with using the button clear selected. So first select the session and then use the button clear selected. And now we want to browse for the next session. So again, browse for VieVS DB. So here again, navigate to the right session. Now it's the 19 March 11 XA session. Edit by using the add button. Make sure that it's here under selected items and click the done button in order to load it here in your process list. Again, make sure that you have here checked this option, use opt file, and the right folder, webinar. We can have another look on the opt file by again doing a right click here on the session and open create opt file. Now the opt file is opening, and again it's empty because we haven't done anything by now, and we will need this opt file later again, but we can close it for now. Okay, so I will not go through models and estimation again because we will leave everything as it is. And we can now go to run and run options. And now it's important that you select these two models again in order to load the observations and to do the new modeling of the theoretical delays. Oops. And now you can type in another name in order that you can distinguish between the two sessions. I will simply take the name of the session. Okay. When we set everything, we can now again start the process by using the save and run button. Now you see that again MATLAB is doing the calculation. This will take some time because we have a lot of scans here. Okay, so you always have already a first result of your session with the chi-squared here. So it's 1.4, that's already pretty good. Okay, now you can again deselect these two modules in order to save some computation time. We can now have a look at our results by going to plotting residuals again. Now we take the right folder and load it. Okay, we see that there to the main, it looks pretty good. It's normally distributed, and also the chi-square is already pretty low. But let's go through the first solution station-wise in order to look for some clock breaks. So there's no jump at Ago. There's also no jump here. Okay. Here at Yargadi, I would say that there are two jumps. There is one here and another one here. Okay, in order to see the jump a bit better, I would suggest again to zoom in. Okay, here we see that the clock, also that the residuals have the drift here, and then they are jumping up and then again. So between these two, there is a jump, which we can add. Unclick the zoom. And again, with the add clock break button, you can detect the clock break. I will do it here. Yeah, sometimes it's not that easy, but yeah. Yes, we want to do it, so confirm it. And now we see that the clock break was added to the opt file. We can zoom out a bit and zoom in again to the other clock break here. Yeah, I would say that here, and then it's jumping down, and then it's going up again. I unclick the zoom, and then add the clock break. I would add it here. That's pretty in between the two, between the observations. So click, and now, yes, confirm you want to add the clock break. Okay, now when we click save and run again, VieVS is doing the squares adjustment again, but now it considers the two clock breaks which we just added. Okay, so we already have here a first result, and the chi-squared is a bit lower, which is a good sign. So we can reload the residuals, and the main solution. So if we now have a look at the first solution and at the station Yargadi, we see that it's now definitely better than before. There are no jumps anymore. But what we can see here is that there are some outliers here and also here. So between this time, there are like outliers. And if we have a look at the main solution, they are also in the main solution. I will now show you how we can exclude these outliers. Okay, for this, go back to the first solution, because here we see it much better, and zoom in order to see it even better. Okay, I would remove from here until here. Okay, for this, it's important that you now unclick the zoom button. So make sure that there is nothing clicked here on the top. And now you have here the section remove time span. And here you can select, and now you can go wherever you want to start removing and press down your mouse. And now you can, with holding the mouse button pressed, you can draw this start and end line. So I will now remove exactly the observations which are within the two lines. And this can be done by clicking on the button remove. So now it's again asking me, do you really want to remove? Yes, we want to exclude it. And now when we have a look at the opt file, so again, I will show you the opt file. Go to the VieVS opt folder, then webinar 2019. And here we have our new session. We see that here in the section stations to be excluded, there is Yargadi with this time span added. Okay, now we can close it again. And we can rerun it by clicking on save and run. So now it's even better, so 1.209. And when we load our residuals again and go to the first solution and to the station Yargadi, we see that the observations in this time window are now excluded, so they are not appearing here anymore. Okay. The last thing which I want to show you now is how you can set the clock reference. Because in VieVS, the reference clock is always set, so there's the clock from the first station in the list, so in this case Ago, is used as the reference clock. And we see that Ago has not that many observations, and it's always a good idea to set the reference clock as a clock from a station which has more observations and where we know that the clock is pretty stable. So I would suggest that we take the station Wetzell, so that we take the clock from Wetzell as reference clock, because Wetzell has a lot of observations and it's known to be pretty stable. Okay, to set the reference clock, this can be done here in the section clocks. Here you have set clock reference, and now you can choose the station Wetzell from the drop-down menu. And now you can simply use the button set in order to set the reference clock. And now when we have another look at the opt file, we see that here that these two lines are added and the clock reference is now set to Wetzell. Okay, so now when we rerun it again, we can see if it improves our solution. Yeah, and it's not improving that much, but still it's improving a bit. It's now 1.200, and we can reload it here. And yeah, so this looks already pretty good. Now, I would say that we are done with this session, but the last thing which should be done is the outlier, so to remove the outliers. And I will show you this again. So first we have to detect them. This can be done by going to Run, VieVS Estimation Settings. And here we can define, or here we can set that we want to do a simple outlier test. Now save and run it again. And we can have a look at the residuals. So now there were some outliers detected. And now, so the outliers are marked with a black cross here. And also always the partner here at the bottom is also marked. Okay, so we want to remove these outliers. So first we have to go to Run VieVS Estimation Settings and unclick this outlier test because we don't want to do it again. But we want to remove the outliers we just found. So go to File, Set Input Files, and click here on the option Eliminate Outliers. And now you can simply run it again. Save and run. Okay, so we see that here again, the chi-squared of the main solution decreased, so it's 1.16. When we go to plotting, residuals, and load it again, we see that the outliers are gone now and that it's now pretty good. Okay, that's all I wanted to show you. And of course, the output, which I just showed you before at the last session, it's the same. You can look at the estimated parameters here, or you can also create a Sinix output using this option, or you can have a look at the MATLAB structure, which is stored in the data directory. Okay, then if you have any questions, you can ask now. Okay, so if there are no questions, thank you very much for listening, and I hope that the analysis went well and you learned something, especially how to use VieVS. Thank you very much.
Thank you.
Thank you. Thank you.
Yes.
Thanks.
Hello, so can you hear me? Okay, so the first part concerning the single session analysis is actually finished a bit earlier than we thought. So our program was calculated to last until 12 somehow, but either you can now use the chance to ask some additional questions that you have, or otherwise we will make the break now as it was foreseen and continue at 1 o'clock, at 13 o'clock Central European summertime. Because if somebody wants to attend only the other part, then we cannot really shift the program now. So, but you can use the chance to ask some questions also, not via chat, but in real voice if you would like to. Okay. Thank you.
May I ask a question?
Yes, please.
Is there any way to save Outlier's information in a file or something like that?
So
Yes, you do save them in a file actually. So
Okay.
when you detect them, when you Helene maybe
Yeah.
can show.
I can show it. So maybe, yeah, I forgot to say this, but thanks for the question. So the outliers, which are found by VieVS, are stored in a file, and I will show you where this file is. So you go to your VieVS, and then here will be you have the folder data, and here you have a folder outlier. And here again, go to 2019, and now there is a file created for this session. I will try to open it with the notepad. And here are the outliers listed which were detected and which were eliminated in a second step. So for example, here the baseline, also the observation between Catherine and Sejong at that time were detected. And here, then the baseline between Sejong and Yolason at that time were detected. So here is a list of outliers, and
And their time. Is there any chance to see that which sources actually they are related to, or we have to dig in the scans details based on the time, then we can find the sources? Or, I mean, this is the only information from the outliers we have,
yes,
correct? The
yes.
baseline and time. Okay, so we have to use this information if we need to see which sources are they. Okay, thank you very much.
You're welcome.
We plan to add the information about the source in the next version of VieVS. We will add a column with the name of the source.
Oh, cool. Okay.
Excuse me, I have a question about the solution output. Is there a way to have a printout, just text format of the solution, the parameter adjustment solution from a single session?
So what exactly do you want to, which information exactly?
The adjustment value. In particular, I'm interested in the clock parameters.
So the estimated parameters.
Exactly.
Okay, yes, you can, I can show this again. When you go to VieVS, then go to plotting parameters, load the session. And now you can here choose, for example, piecewise clock for example, let's say cookie. And I remove the error bars to do it that we see it a bit better. And now if you want to export this information, I think that's what you wanted, right?
Correct.
You can save this in a text file by using this button here.
Okay.
And then you I will just name it somehow. And then it's saved, or it's stored in VieVS out, and here, that's the text file now. And when you open it, there is the information for all the estimated parameters for the clock listed. So over is the time, the value for the estimated parameters, and the standard deviation. I now chose the antenna cookie, and here you also have the unit. It's in centimeters. So you can also use this information later. Did this answer your question?
Yeah. Is there also a way I can have information about the quadratic model? Is that recorded somewhere?
I'm not sure about this, but maybe secret.
Oh.
Do you know this? So no,
Okay.
that's not.
Perhaps I can comment on this. That's a good question. It's not really easily available, so you have to build it with the X underline files.
Mm.
So
I see. I see.
It's a good point, but yeah, it's not readily available, so you have to build it somehow.
Okay, thank you.
I have two questions actually. The first one is like in the last example, the improved chi-square value was almost 1.129 or something like that. So what's the threshold of chi-square when you evaluate any observation? Like how much you can improve a chi-square value, and when do you make a decision? Okay, so that's it. Like I can't go below that value.
Mm-hmm. So yeah, I would say the goal is like as close as possible to 1, but yeah, sometimes it's not possible to improve it anymore. So it's always a question on, for example, yeah, if you fix all the clock breaks, and then it's, yeah, so it's always a question on how many, so you can also exclude observations, but if you exclude observations, then you're also losing information. So it's always a question on what you want.
So is it possible like you fix everything and then you run a couple of times and then you will notice like the chi-square is not decreasing, then you just decide, okay, so that's it, I can't go below that chi-square.
Yeah. Mm-hmm.
And the second question is regarding the theoretical delay of any source.
Mm-hmm.
Like how do you calculate a theoretical delay value from, I mean, for any source in one observation? Let's say I have 36 sources in one observation and I want to calculate a theoretical delay for a specific source in that observation.
Mm-hmm.
Let's say which will be like in picosecond unit or something like that.
So you want to have a look at the theoretical delay for one source, for example?
Yes.
Okay. I'm not sure if this is possible. Maybe my colleagues?
Well, I don't think that it is readily available somewhere. Then you would have to do something with the source code and make yourself an output of this information. Of course, it is there, but I'm not sure if you find it somewhere in the stored data. Maybe somebody else of our team knows.
I think it's in the level 1 directory where we store the results in the scan array. So you should load the scan array into MATLAB, and there you see the theoretical delay computed. And then you have to filter on your own the information for one specific source.
Oh, okay. Thanks, Anna.
Excuse me?
Try to show this.
Yeah,
the file.
Yes. Yeah, can you please show this?
Yeah, I can understand the survey about the PWL. Can I give me a screen share?
Yes,
Can you hear me?
Yes, I will just show what was just said about the level 1 data. So you find this data here, VieVS data, and then level 1, and again the subdirectory, and here is this information stored again in a MATLAB structure. Mm-hmm. But
Okay, and then which file to use to extract the information regarding the theoretical delay value? Like.
mm-hmm. So maybe Hannah, do you know it again?
It's in the scan.
In the scan, okay. In this file here.
Okay, maybe can you open that file
Yeah.
if it's possible?
I can load it.
I think in ops, you go, yes. And then it's this com is computed.
Aha, that's computed. So, and this
Oh,
column.
Sorry, can I ask some questions?
Yeah, of course.
I can't understand so well about the PWLO. Can you give me a screen share?
Yes.
Okay. Yeah. Can you give me the right of the screen share? Yeah. Oh, sorry.
So you
Where
should
can
be
I
able
share my?
to share your
Yeah.
screen now. Okay.
Okay. Okay. Wait a minute. Yeah. I just want to ask about the PWLO and the two questions. I can't understand so well how to ensure the condition is met. Can you get a screen?
So are you, do you talk about the constraints?
Yeah.
Okay, for the constraints. This is not a hard condition. So it is not a hard condition in a way that it has to be true. It is just a statistical meaning, a statistical way to say how much you allow the estimated parameters to diverge between two estimation intervals, epochs. So you can't say this is, everything has to be lower than 1.5. It's more like on average 90% or 65% need to be lower than this 1.5. So it's not a hard cut.
Oh, okay. Thank you. Can you answer me the question 2 about the difference value of the 0.1 and 0.2? Is there any constraints about the difference value?
The thing is 0.1 and 0.2, typically they are only one. So you estimate, I think you have some, or probably I'm misunderstanding something, but probably you are also misunderstanding the concept of piecewise linear offsets, continuous piecewise linear offsets. So what we are doing is we really estimating parameters every, let's say every 30 minutes and get one estimated parameter every 30 minutes. So at the same time, what would be your 10, for example, you don't have two estimated points, but only one.
Oh, okay.
So
maybe I misunderstand about it.
Yeah.
Yeah.
So yeah, if you have a situation like the one you're showing here in this example, you will definitely get a problem using piecewise linear offsets here because you don't have a continuous line. So that's more an indication of you need to add something like a clock break or a hard break here, but not a continuous piecewise linear offset.
Okay, I got it. Thank you.
Okay.
Thank you.
I mean, you can find more information about piecewise linear offsets on our wiki page. On our wiki page, we have an introduction to VLBI, and there we also discuss piecewise linear offsets in more detail.
Okay, thank you.
Okay, are there more questions? Because if there are no more questions right now, then I would say we will make a real break now, and we will see each other in 75 minutes. So long.